Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Shrigyan Brachamari.
Right.
Yes.
Yeah.
So he is a first-year PhD student at the ECE department of Duke University. His co-advisors are Iman Marvian and Henry Pfister, who they're broadly working in the field of quantum information theory. He was previously a research assistant at CQT under Marco Tomo Michel. And he did his undergraduate and master's, okay, so undergraduate in mechanical engineering, in fact, and master's in quantum engineering at the Indian Institute of Technology in Madras. So today he will be telling us about this fixed point algorithm for matrix projections. So yeah, Shrigyan, the floor is yours.
Thank you, Gallo. Okay, everyone can see my slides now, right?
Yes.
Okay, great. So I'm going to try to keep
it's not in full screen. That's intentional.
Right. Yeah, I think I want to keep it this way. If everyone
Sure,
can see it.
yeah.
Okay.
I think
I'm
it
going to try
should
to
be
keep
fine.
this. Okay, great. I'm going to try and keep this conversational, and because I'm going to try and go through some of the proofs. So, and there's going to be a bunch of equations. So anyone who wants to interrupt me, please interrupt me as often as you want, because I might get carried away. So like Gallo told you about me, I'm Shrigyan, and the research that I'm going to talk about right now was done in CQT mostly with Roberto Riboli and Marco Tomo Michel. Roberto Riboli is, I think, fourth-year PhD student now with Marco. He works broadly in quantum resource theories. I'm assuming all of you are familiar with Marco by now. So okay. So the way I'm going to go about talking about this project is sort of how we came to think about the problem. It's essentially a specific a conditional max entropy type quantity, which we are interested in, and optimizing that can be quite difficult. And what we come up with is a fixed point like recurrence type algorithm, like a map, a recurrence map, and we prove that it converges, and it converges exponentially fast. In our paper, we do numerical simulations. This sort of algorithm can also be solved using semidefinite programs. Semidefinite programs are usually quite nice. If you have any function or like metric in quantum information, if you have a semidefinite program, typically people just call it a day and they say that they're happy with it, because convergence can be provable. The issue is, in practice, SDPs can be hard to actually perform in a computer, especially when the dimensions get larger, and such is the case in this problem. And we will show that in our numerics, which you'll see later on. And therefore, for this quantity, we sort of show this recurrence algorithm, which does much better than the SDP. The motivations for this thing comes from optimal transport. I'm going to start talking because you're already seeing the slides. So this started in CQT when Chris Ferry visited CQT, and he discussed this paper, which him and his PhD student Afam had been working on. So what they recognized was there's this problem called matrix barycenters, which I don't really understand in optimal transport, with a good deal of literature, which basically dwells with the first equation that you see on this slide. I'm not sure about the interpretation they have, but Chris Ferry and Afam realized that this has a very nice quantum interpretation, and the interpretation is the following. Let's say you're given some state rho, and that rho you don't know what it is, but you know it can be, say, some state rho 1 with probability p1, some state rho 2 with some probability p2, and so on and so forth. Now your aim is to find some state sigma which will maximize the mean fidelity. So in some sense, you're trying to figure out, is there one state which is like closest to this state, of course, in terms of fidelity. And this expression essentially captures that. It captures sort of like the mean fidelity of some sigma that you're choosing for each of these possibilities with a weighted probability, and you maximize it. So far, so good. There are a lot of ways to try and solve this, including SDPs. But one method that has been a lot of analysis has been done in operations research for the past 10 or so years is this fixed point algorithm that I've written over here. Essentially, it's this, right? You start with some seed sigma, some density matrix, and you perform this map multiple times. So sigma, k of k sigma, so on and so forth. And you get a sequence. And what the literature shows is that not only do you converge to the optimal, you can converge to it exponentially fast. And there's been all kinds of analysis. People have used all kinds of tools. They've shown that they've worked on the dimension of the scaling and all of that. So yeah, it's a well-studied problem in operations research. Now, well, we saw this problem, and it was quite nice. This idea of having a map-based algorithm as opposed to your SDP or gradient descent. It's quite nice, and you want to explore it. The first thing we observed, though, was that this particular problem can be written in terms of a conditional max entropy, except as you can see in this last expression. And by the way, I'm just showing this, and if I'm slow or something, somebody please tell me. If I'm too fast, I'm going to discuss it. So I'm counting on you guys to stop me. Yeah, so we realize that this first expression can be written in terms of a conditional max entropy, where except that rho has to be a classical quantum state, where the register I will have the quantum state rho I with probability pi. So that's what it can be written as. So far, I've done nothing. I've just written it slightly differently. And the existing research already tells us that such a conditional max entropy problem for this specific classical quantum states can be solved with this algorithm. And that's quite nice. But the first question, like when you write it in this form, the very next question that you would think of is, okay, sure, it works for classical quantum states, but does it work for general states or not, right? So that was the first thing we did. So yeah, we took the same expression and we asked, okay, we know it works for classical quantum states. Can some version of this map do the same thing for general states? And we found that yes, we can. And the general expression is something like this. So right now, I know this map seems kind of strange. You don't necessarily need to look into it too much. I'm going to discuss it in more detail for the more general class of problems very soon. Yeah, but I just want to point out one thing, that the expression in the center over here is like a geometrical mean of two density matrices. And yeah, so that's how this was our first result, right? And this was quite nice, except that it's still quite limited. Conditional max entropy is a nice quantity for a lot of things in quantum information, but yeah, it just feels like this idea of these algorithms has a lot of potential. So for a long time, we were stuck with this. We knew that we have this conditional max entropy problem for general quantum states rho, and we could do this algorithm. And it was kind of limiting. But then later, so I made this observation. Now I'm going to first I'm going to take a segue and talk about how this observation happened. So say you have some quantum state sigma AB. Now, if you do a twirling channel, and if by twirling channel, I mean this, you have some group of a unitary group, and if you pick any one of these unitaries randomly and perform the unitary on the quantum state, what you're doing is a twirling channel. And from something in representation theory called Schur's lemma, we know that if your unitary group is such that each unitary is UG tensor I, where UG itself forms a irreducible representation, then you end up getting identity by D, so noise tensor sigma B, the partial trace. Honestly, the takeaway I don't think is really important for people, in case they aren't familiar with this, to think too much about the representation theory. What I'm really trying to say is the partial trace of a bipartite quantum trace sigma B can be written as like a twirling channel acting on a bipartite state, and there exist certain unitary groups where this is possible. So this was the observation that we had. So next, we thought like maybe a better generalization of the problem is, okay, so right now we know that this algorithm that we have, it works for a specific kind of twirling channel, which basically is partial trace. It gives you identity tensor sigma B. So is it possible that the same algorithm would work if you do some general unitary group twirling? Again, I've written the notation over here. I just want to stop here and ask: are there any questions? Are people following what I'm saying? Hello?
I think I'm fine for now. But can you go back a bit to the last time?
Sure. Yes.
Yeah, because I mean, I think I saw like you had a max here, but previously you have a min. Did I?
Oh, did I write a min? Oh, sorry. Yes, that's a typo. I'm sorry. That's supposed to be a max.
Okay. So which one is the correct one? Is it?
It's max. It's max.
Oh, it's always max. Okay.
Yeah, it's always max. Yeah. I'm sorry. It's all max over here until much later, and I'll point it out then. Yeah. Sorry about that.
Yeah, it's fine. Yeah.
Okay.
Yeah, I don't know if anyone else has some questions. Yes, I guess you can proceed.
Okay.
Oh, sorry. I just want to make sure the unitary group you're considering the very general one, or is there any concern on the unitary group you want to discuss for specific properties? So you will change the discussion of the unitary group.
Right.
I mean,
no.
Yeah.
this is for general unitary groups. Like what I was saying was, in the conditional max entropy can be interpreted as a very specific unitary group. But what we are about to show now is this optimization problem works for general unitary groups. And by the way, I've written finite unitary groups here, but I think it works for infinite as well.
Yeah, and if you are discussing specific quantum state, for example, can you constrain the group you are talking about?
Okay. So there are a bunch of things which we have looked into. Right now, I'm not thinking about specific groups. Right now, whatever proof I'm going to do and whatever I'm going to discuss is true for all unitary groups.
Okay.
Yeah, but I can give some examples towards the end where I'll talk about how specific unitary groups can give you some known examples. For example, fidelity of coherence, which basically says if you have a quantum state which is incoherent and you want to find the closest coherent state, such a problem can also be thought of as, you can pick a certain unitary group and that will simply be like the powers of Z essentially. If you pick such a group, then you can, it will become the fidelity of coherence. So there are a lot of these examples. And for example, in the qubit case, right, the one I just discussed, or in the general case, sorry, if you were to pick, if UGs were the Heisenberg while operators, then that would simply give you conditional max entropy. Yeah. So, but as far as all the work I'm going to discuss next is concerned, you can take any unitary group you like.
I see. Okay. Okay. Thank you.
Yeah. One thing I want to clarify is this notation epsilon dot is just a twirling channel, and it's good to keep it in mind because I'm going to use it.
Sorry, you said that if the unitary group is Weil-Heisenberg operators, then you get conditional max entropy.
Yes. Yeah.
Okay. I see.
Yeah. I mean, that's one example, by the way. There can be many. As long as you pick, so essentially it has to be a one design. If the unitary group you're picking is a one design, you will get conditional max entropy.
Okay. So I think Pauli's are one design, right?
Exactly. So Pauli's are also going to be. And to be fair, Heisenberg while operators are like generalizations of Pauli too, right?
Yeah, that's true. Yes.
Yeah. But you're right. You can pick any one design you like, and it will give you conditional max entropy.
Okay, but then so let's say what kind of twirling channel do I have? Let's say I have Werner twirling, something like this. Is it obvious what it means in those cases?
I'm actually not sure about what Werner twirling is right now.
Okay. I mean, Werner twirling is really just you're applying sort of U tensor U, tensor U. Okay, depending on how many. Okay, if it's by part like this U tensor U symmetry.
Yeah, no, it's not obvious to me because U tensor U will not be a one design. It will have multiplicities involved, and the answer won't become obvious, I think.
But in any case, the optimization sort of becomes some kind of computation for the rho.
Yeah, true.
Scale,
it will work. Yeah. So absolutely.
But maybe what it means depends, of course, on what the twirling means.
Yeah.
Okay.
Right.
Okay.
Right.
But do you have other examples where you know what it means?
What a twirling can mean. So in the case of the fidelity of coherence, you pick these powers of Z, and what essentially happens is you take like a diagonal matrix, a coherent state.
Yeah. Okay, I see.
Yeah, so that's one example I can think of.
Yeah. Okay. Yeah. Okay. Maybe I have interrupted you enough.
No,
so you can continue.
Sure. I'll continue. So this is what I was saying. So natural generalization now is the following problem where you want to maximize the fidelity. You want to find a quantum state which has maximum fidelity with rho, except that you twirl the state first, right? So that's one problem. Another equivalent form of this problem is, let's say you have been given some unitary group and you're given some state rho, and you want to find symmetric states. And by symmetric states, I mean sigmas that commute with UG. And you want to find for a given rho, you want to find the sigma, which is the symmetric sigma that is closest to a rho in terms of fidelity. I'm not going to actually explain why this is true, but it's kind of a simple exercise. I think if you just put some thought, it'll be clear. I'll give a few hints. If something is symmetric already, then acting the twirling channel on it will not make a difference. It'll give you the same thing. And the second hint is that if you twirl a channel, a quantum state, and twirl it again, it makes no difference. Like twirling once makes it symmetric. So if you keep twirling it, nothing will happen. So if you take these two ideas, it'll kind of be apparent why these two problems are the same. Okay. So next, so far I've just been telling you how we converge to this problem. I want to like give a valid operational meaning to like validate why we bothered doing this. So imagine you're in an experimental lab and the scientists can prepare quantum states, except that the lab and everything has to respect some symmetries, which is very common in most physics situations. So, and therefore the quantum states they can prepare are only symmetric states. And like just in physics, symmetries are typically defined by a unitary group. Like in this case, every quantum state should commute with every element in the unitary group. So now a customer comes and demands some state rho to be prepared. Now, if the state rho is already symmetric, great, you can prepare rho exactly. But if rho is not symmetric, then the question becomes, what is this closest symmetric state in terms of fidelity? And that can be a difficult computational problem, at least. So what this algorithm offers to the scientists in this lab is a quick, efficient way to find what state to prepare. And it also tells you how close it is to rho. So that's the operational meaning. And later on, we found out that this particular problem has been studied separately as well. So in a paper by Mark Wilde and his PhD students called Testing Symmetry on Quantum Computers, they studied this particular problem amongst like 2 or 3 other similar symmetry-based fidelity functions. So they provided an SDP for the same problem. This is not too relevant for what I'm going to talk about, but I'll just tell people a bit about it. The semidefinite program is the idea behind their derivation was simply like using the semidefinite form given of the fidelity function given by Waterhouse and Killoran. I think they did this separately in 2010. Yeah, so once you have that SDP, once you know about that, it's very easy to like make a small modification to include like the symmetries, and you get it. Unfortunately, while this SDP will absolutely work, it scales terribly with dimension, and it's not necessarily a very practical way to sort of find these states. And I'll discuss this a little bit more, the efficiency with plots a little later. Okay, so I'm just going to state what we are doing here, like what our algorithm is, and then I'll discuss more about how we come there. So imagine instead of rho, I've called it R. You give me a positive definite matrix R, and you start by some seed. In this case, we pick a very specific seed, and there are some reasons there, but I think it's a bit too involved for this discussion. So as far as everybody's concerned, just pick an initial seed S0. And then you perform this map and multiple times, like n times. So you get S0, you perform the map, you get S1, S2, so on, Sn. And what we claim is Sn will be very close, for large enough n, Sn will be very close to the optimizer to the problem. Okay. Epsilon, again, remember, is a twirling channel. You twirl it over here, you square it, and you... Okay.
I have a quick question.
Yes.
So for the seed, you said like you can take 0. But wouldn't that be like not a valid density matrix?
Oh, no, I didn't say 0. I said you can take any seed. It has to be a density matrix.
Okay, but it could be any.
Yeah, it has to be a valid density matrix. Like
Okay,
it has to be, trace should be 1, it should be positive semi-definite.
Ah, okay. Sure.
Yeah. So the reason why we pick this seed is because we know it's going to be kind of close to the solution.
Ah, okay.
Yeah, because of a different entropy. Anyway, it's not important. Okay, so so far I've like just given you guys this slightly strange kind of map, and there's no reason to believe why it's true. So I'm going to like tell you guys how we came up with this map. So again, I'm stating the original problem. I've written the fidelity in its usual like algebraic form. That's the first equation. So notice that what are the constraints here? It has to be any density matrix, which means it has to be positive semi-definite, but it also has to be trace 1. So it's a constrained optimization problem. For the way I'm going to motivate this, we prefer it to be unconstrained. So I'm going to show you how we unconstrain this problem. So for a second, just forget about the thing I told you and just look at the first equation over here. That's a separate optimization problem. It's a minimization. It's trace of twirling of sigma minus twice the fidelity. So the second equation follows from the fact that twirling, like any other CPTP map, is trace preserving. So you just end up getting trace sigma and minus twice the fidelity rho epsilon sigma. But remember, right now, this is not on density matrices. This is on any positive semi-definite matrix. So I can do a trick. And the trick is that I can split this any general semi-definite matrix into a normalized form and then k, the normalization factor. Like sigma can be written as k sigma tilde. Sigma tilde is like a density matrix and k is some non-negative number. And when you do this, it becomes this expression. Like trace sigma simply becomes k, and you pull out root k from the fidelity. What you can do now is you can keep the minimization on k outside, and you can put the maximization. The maximization on terms of on sigma tilde goes inside. So like just from this form, you realize that if you can solve this unconstrained optimization problem, and you'll end up getting some sigma, and if you normalize that sigma, it will be the solution to the first problem. If again, I think this was also a little quick. So if anyone has questions, I'll clarify right now. What I'm basically claiming is if one is interested in solving this problem and they find some sigma, which is the minimum for this, it will not be normalized. But if you were to normalize it, it will be the solution to our original problem. The only reason we care about this is because it's unconstrained, and I'm going to take a derivative next. If this is clear, it's fine. But in case this is not clear, one can like not bother about this and just think that I'm taking like a derivative of the original function using like a constraint like KKT conditions and taking the derivative. And I'm not going to discuss how I take the derivative. It's not too important. You take the derivative with respect to sigma, and sorry. Okay. So once you do take the derivative, you get an optimizer condition, and the optimizer condition is the following. So if sigma is any sigma, which is a solution, will satisfy this. You twirl sigma, and then you it should be equal to the quantity to the right. And in the next equation, I've just squared it and divided by epsilon sigma on both sides, to the power minus half on both sides. And all I'm saying is this is the derivative, and the second is also essentially the derivative. And if you have any optimizer, it should satisfy both of these conditions, because both of these conditions are equivalent. Now further, we know that this function is convex. So if you have a solution that satisfies this condition, it's not just a local optimizer, it's a global optimizer. So if you can find a sigma that satisfies these, you're done. You found the solution. Okay. So what we do next is you have like a fixed point equation like this, and you know if it satisfies it, you're good. So our idea was now to take this particular like map and do it iteratively. So the hope is that the first time you do it, you will not end up getting equality. But if you keep doing it, you will eventually converge. And if you converge, you know that the sigma going through this map will give you the same thing. So you'll have the answer. That was our hope. And we found that to be true, and we proved it as well. But let me just write that down, right? You took that map, you started with some state, and you kept doing this. Notice that I have not twirled everything again, and the reason is the following. If you start with a state that is already symmetric, this map will give you a symmetric state. So twirling a symmetric state doesn't have an effect on the state itself. So it will just stay the same. So we've removed some of the epsilons, and we've just created like a sequence of this form. Also, it's easy to see that the solution that exists a solution that is symmetric. So we're not too worried about like, oh, you're only looking at symmetric states in the sequence. What are the solutions not symmetric? Because it's easy to argue that the solution will in fact be symmetric. So we have this map, and what numerically we found now that yes, it's actually giving us a solution. We compared it to SDP results, and we found that it's giving you the solution. So we wanted to now prove it, just like they have in the operations research community. Where, by the way, the problem they did is now is a very, very, very specific form of what we're doing here. So we were hoping to generalize it to this, and we managed to do that, and I'm going to talk about it in a bit.
Okay, I just have a question. So when you say that you know that it gives you the solution, you compare it to the SDP.
Yes.
So is it the case that the solution is unique?
Yeah, in this case, the solution is in fact unique. I think it's because it's convex.
Oh, okay.
Yeah, the solution is in fact unique. Well, okay. The symmetric solutions are unique. You can perhaps construct non-symmetric solutions which are not unique, but we're only concerned with symmetric solutions. And I think only symmetric solutions exist. So, yes.
And like, so I guess you know this for sure, so you can prove that the solution is unique.
Yeah, I think using convexity we had proved. Right now I can't like off the top of my head prove it, but I think yeah, using convexity we proved it.
Okay. I mean, basically, I sort of like, I think like with SDPs, it's not obvious whether it would have a unique solution or not. Yeah, but I guess, I mean, just from the structure of your problem, maybe you know you have some extra information that tells you it has to be.
Sorry, I don't know. There might be a very simple answer to this question, but I'm not like thinking of it right now.
Yeah, I mean it's fine. Like it, yeah.
Yeah. Okay. So this is like sort of the details of how the proof is going to happen, but I'm going to skip this slide for now and talk about like our basic proof technique and come back to this if we are still interested. So before that, I want to introduce like a quantity. So ignore equation 3. Start from equation 4. I want to introduce this quantity called Bures distance. Bures distance, as far as we are concerned, is like it's essentially a metric for positive semi-definite matrices. Let's call them A and B. It's trace of A plus trace of B minus twice the fidelity of A and B. And it's a metric. It follows the necessary conditions of like a metric, including the one that we will use. That if Bures distance between two positive definite matrices is 0, it means both of the matrices A and B are also 0. Okay. Now, the part that I just skipped was proving equation 5. And the reason I'm doing this, I want to explain why proving equation 5 is sufficient to like at least show convergence. And what does equation 5 state? It states the following. You start with some state sigma and you do the map once. And the Bures distance between those two states is always lower bounded by the difference of the Bures distance between sigma and the state rho, and minus the Bures distance between rho and k of sigma. So this is something we have proved. I'll discuss that later. But I'm going to explain how this is sufficient for us to prove what we want. So then, now if we like take some random seed and like construct such a sequence using the map, then for any sigma n and n plus 1, this equation is true. B of sigma between sigma n plus 1 is lower bounded by the Bures distance between sigma n and rho and sigma n plus 1 and rho. And now I think people can see if you were to write all of this down in terms of all the n and add it up, you'll have on the right hand side you'll have a telescopic sum. Let me show you what I mean. So if you were to take that sequence and add all of them up, on the left hand side, simple. You just add up like for all n Bures distance between sigma n plus 1, and it's lower bounded by this like they cancel out. So Bures distance between the initial seed and minus like where you ended the sequence, right? And honestly, you're already kind of done with what we wanted to prove. Like because here's on the right hand side is a bounded quantity, and I said Bures distance is always non-negative. Rho comma sigma 0 is some quantity. Worst case, also your Bures distance will be some it might even be 0. So you have some quantity to the right. And if that is true, this sequence as n tends to 0 converges to some quantity. By the way, you can be sure that this quantity is positive. I'm not discussing it here. It's not relevant for the slides, but the right hand side will always be positive. Anyway, so you can show that this summation of Bures distance in sigma n plus 1, sum over all n, will converge to some positive quantity. And that from there, you can argue that as n tends to infinity, the Bures distance between sigma n and sigma n plus 1 goes to 0. Therefore, eventually sigma n converges to sigma n plus 1, which means that you have you have found a state where the recurrence relationship is satisfied. And the map doesn't give you a new state, so you have found like it's converged. The map has converged. So this is actually it. This proves that the map converges to the optimizer. We actually go another step further, which I'm not discussing in this slides. It's that using this quantity, this expression 7, we can also, and something called the the PL inequality, which is essentially the strong convexity of fidelity function. We can show that not only does it converge, it converges exponentially fast. So that's something people can look up in the paper. It's a lot of details, which I don't want to get into right now. Okay. Have people followed me? If I can now go and discuss how I prove this. How I prove this quantity 5, this expression 5, or I can just like wrap up and show some numerics and motivations and continue. So up to you guys.
Because I think like it's not immediately obvious to me that it converges, because it's not obvious to me that the distance between like let's say rho and sigma n and sigma n plus 1. So like this, like in the 6. So on the right hand side. So
let me go back. Yes.
So in some sense, like you're saying that you would be able to see that as you increase the n, this kind of difference shrinks.
Yeah.
But that's not immediately obvious.
No, that's not what I'm saying actually. I'm saying that so any sequence, any summation from 0 to n on the left hand side is always upper bounded by let's just say rho comma sigma 0, right? So you have like a sequence, so you have a series whose summation, like the sequence, is always upper bounded. So therefore, like at some point, the quantity which you're adding should tend to 0. Otherwise, it will just blow up, right? It won't.
Okay.
Yeah, that's the logic.
So for follow-up question, even the sequence of sigma n and sigma n plus 1 converge, it doesn't mean it is converged to the true row you want to find.
It actually does, and the reason is that as I explained before, so if sigma n converges, so let's just say that for some n, sigma n is equal to sigma n plus 1. Won't actually happen, but just humor me. If sigma n is equal to sigma n plus 1, in that case, the map, when you act that map on sigma n, it gives you the same solution. And as I explained before, that's just a derivative condition. Like this map is built in this way, that if your sigma n plus 1 is equal to sigma n, it just means it satisfies these equations, which is the condition for optimizers.
Oh, I see.
Which we get from the derivative. Yeah. So if you look at the second equation, that's essentially the map, right? So if you have a sigma n that's equal to sigma n plus 1, it's just telling you that sigma n plus 1 is still equal to this thing. But if you like do some basic algebraic manipulation, you end up getting the first equation. So it means that it's satisfying the derivative, the optimizer condition. So therefore, if you do like, it's kind of, this is how we like did it. We did it intentionally this way. Like we started by the derivative condition and built a certain map, which will like, if it converges, you know that it's the solution. And then we showed that we proved that you can show convergence. Like that's how it was like built. It's not an accident.
I see. So is there any requirement this sigma must be normalized, because you say you relax the normalization condition, right?
Yes. No, sigma does not have to be normalized.
Oh, I see. Okay.
Yeah, and like actually, it's easy to see why. If you look closely at this equation, if you were to take like, so you start with some sigma n, right? You multiply it by some factor 5. Like the factor will cancel out because you have 5 here, square root of 5, square root of 5, and then you do half. So again that, and then you square it again. But then that factor is here too, right? So I'm just saying that factors will cancel out. Let me say that again. You start with some sigma n, you get some sigma n plus 1. If you were to start with like say 10 times sigma n, the sigma n plus 1 that you'll get will be the same thing. That's just the kind of expression that this is.
Oh, see. Thank you.
Yeah. Okay. So if everyone's like following, I can maybe. So far I just told you to accept equation 5, and yeah, maybe I'll just, since we have the time, I want to leave like, I don't know, 10-15 minutes at least for questions or discussions. I'm going to talk about the proof before I go to numerics, etc. So equation 5. So equation 5 is what I want to prove now. And by the way, remember, Bures distance is just like trace of A plus trace of B minus twice fidelity. So if you were to expand it in this form and just do some basic, algebra, you'll get equation 3. That fidelity of rho, comma, k sigma is greater than or equal to trace k of sigma. So if you prove 3, you've proven 5. And I'm just going to give you like a sketch of how I proved 3. I'm just telling you the tool that I used to prove 3. So this is like a general property of the fidelity function. The fidelity of, if you can write your matrices rho and sigma as A dagger and CC dagger, ignore the half here, by the way, I'm sorry about that. In that case, you can write the fidelity of A dagger, CC dagger is just the trace norm of A dagger C. And using Folder's inequality, you can show that this is lower bounded by the trace of A dagger C. And now, if you all we have to do is cleverly pick A and C so that we get what we wanted. So if you pick A as such, like sigma 10 to the power minus half and the geometric mean, and C as like the twirling of the geometric mean, then you find that A dagger rho is equal to rho, CC dagger is k of sigma, and yeah, the trace of A dagger sigma will simply become yeah. Anyway, if you insert A and C into this equation, this A and C equation 2 into the above equation 1, you end up getting equation 3. It looks simple here, but it took a long time to like figure out how to prove this. So that's a general idea how we prove 3. And after 3, if you do some basic algebra, you end up getting 5. And then you have this property, and then the rest of the proof just follows. Okay, so this is kind of the end of the proof for convergence. I'm not discussing the proof for exponential convergence. You just have to take my word for it. It's in the paper. it uses the same equation, and then it uses strong convexity of the fidelity function. All right. So now, as I think somebody asked me before about the applications of this. So one of them is fidelity of coherence. I think I discussed this. In this case, you just pick a unitary group, which are the powers of Z. If you pick this, then if you take like the you find twirling channel, which are the unitaries are the powers of Z. It takes some quantum state any density matrix and just gives you the diagonal. So yeah, essentially you look for any, if you use this unitary group, what you're looking for is for any given state rho, find the closest diagonal state, which is the fidelity of coherence. This is one well-studied example in resource theories. Then, of course, max conditional entropy, which I already discussed. And then comes geometrical measure of entanglement of maximally correlated states. I don't know too much about this, but essentially it's a function. It's like it uses max conditional entropy anyway. So if max conditional entropy is true, then this is also true. Now, quantum mean state problem. Quantum mean state problem was the first problem I discussed, like the one I told you guys about the optimal transport thing. It's essentially where the quantum states are classical quantum, and the unitary group is one design. In that case, you end up getting the quantum mean state problem. To remind you guys what that is, if you have some state, quantum state rho, and you don't know what it is, it can be rho 1 through rho n with probability p1 through pn. You want to find out some sigma which maximizes the average fidelity. And finally, we have quantum error precompensation for group twirling channels. And I'll explain what that is. So imagine you have an experimental setup where you know that you can feed any quantum state of your liking through a channel, but it has to go through this channel. You know what the channel is, and your hope is to prepare some given state rho. It's possible that preparing rho is not possible. So in that case, what is the state you should feed into the channel so you get as close as possible to rho? So since we're talking about, in this case, if you are considering only group twirling channels, then it solves the quantum error precompensation problem also. So yeah, these are the applications we're interested in. I mean, we know of. We're still interested in more applications. And something that I haven't discussed in this because we don't actually have evidence, but like we don't have a proof. So throughout, I have been looking at fidelity-based functions, right? And but numerically, we also studied a larger class of entropies. We looked at conditional alpha Z entropies, and numerically, we found like a certain, like some modification of this map also works, but we just don't know how to prove it. I mean, we think it works because it's numerics, of course, but yeah, the proof is not clear. All right, so that's the end of the applications. Sorry. So I just want to show you guys some numerics. So I considered two of these problems. One is the max conditional entropy and the fidelity of coherence. And we compared how our algorithm does to the semi-definite program suggested by Mark Wilde. And these are, you can just look at the means, and you can, the x-axis is the dimension of the problem, where the quantum state is a two qubit state, and this is just like the dimension of the qubits. And as you can see, by the time you reach, there's a massive difference in how much time it takes, even the max conditional entropy problem. Like, by the way, the scale on the y-axis is a logarithmic scale. So by the time you reach like 6 dimensional qubits, our algorithm will take like 10 to the power minus 2 seconds, and the SDP will take like almost what 10 seconds or something. Yeah. So it scales pretty badly, relatively. So yeah. So that this sort of tells you like why we care about these kind of algorithms, because they're very, very fast and quite efficient. Also, another thing I should point out, I stopped with dimension 7 because my laptop cannot handle, I think, any greater dimensions for the SDP. It can for my algorithm though. And you see similar results of fidelity of coherence as well. Yeah, I mean, thanks guys. This is what I had to show you. If you guys have questions or anything to discuss. Yeah.
Oh yeah, yeah. Yeah, maybe I shouldn't have interrupted you because I wanted to ask questions. Okay, but anyway, I guess, yeah, thank you for the wonderful talk. Okay, so let me just jump to my question.
Yes.
So you said, like, I mean, in your plot, you stop at 7 because of the SDP part, because you're, of course, doing a comparison. But if you just use your algorithm, how much further can you go?
Okay, I haven't exhaustively tried because it gets so slow, but I think you can definitely go to like dimensions 11, 12, 13.
Oh, sure. Okay, I see.
Yeah. Yeah. I haven't exhaustively tried it though, so I can't really tell you where we stop. I think it should be easy because what we're like the map itself is not like very complicated, right? And like MATLAB or any like good programming language can handle pretty large matrices. It's possible it might take time, but it won't entirely crash. Like in the case of SDPs, they'll just tell you that it's too big and like memory has run out. In this case, the memory run out is not an issue because it doesn't. Yeah, I guess this is a good point which I don't bring up. I suppose more than it being like time efficient, it's also quite memory efficient.
Okay, yeah.
Right?
Because, yeah, I think like for my SDP, when I run things, usually my problem is I don't have enough memory, and then I just cannot do the calculation.
Yeah, exactly. Actually, you're right. You're right. I should have. This is exactly what I should say from now onwards. It's not that it's time efficiency is of course nice, but it's the memory efficiency where it like really excels. Like memory here is very little, whereas SDP's memory runs out very quickly. So, yeah. Yes. Okay, everybody. That's the thing which I want to tell you guys, which I should have told you before. More than time efficient, it's a very memory efficient algorithm.
All right. Okay. So now I want to see. Yeah. Okay. So if anyone else has questions, you're free to sort of unmute yourself and ask.
So I have another question. So in the figure you show the runtime efficiency, but I assume that these two algorithms, SDP and your fixed point, they give you the same state? Are they giving you the same answer? Okay.
Yeah, I checked that.
Okay, good.
I mean, obviously up to like some numerical accuracy, like 10 to the power minus 10 or something, but sure.
Yeah. And then your next step is to try those other like alpha type of entropies.
Yeah, I mean, I don't know if I'll be working on it, but I think conditional alphas and entropies would be a nice thing to prove.
Okay.
It's kind of hard to prove, I think, because like you see, like the main step that I did, I used that fidelity property. I used that property of fidelity where you can write it as, the trace norm. A similar thing doesn't exist, I think, for other alphas and entropies, as far as I can tell.
Okay. Yeah. Okay.
Yeah.
But it's likely because some of those alpha Z entropy, they have some fixed point properties as well. So it might be worth to try. Yes.
Okay. Yeah. I mean, maybe just mail you once and we can discuss that.
Yeah. My student Hao Zhong would be like my former student Hao Zhong Chen would be an expert on that. He like
actually Hao Zhong worked on this. Like when I started this problem, he was visiting. So when we were trying to prove the conditional max entropy, he was around for 2-3 days. So we were all trying to solve that problem. Yeah.
Okay.
Yeah.
Good.
Actually, we were discussing another version of this problem, a double optimization with Hao Zhong for a while. I guess then I moved to a different group and everything, and people just got busy, so whatever happened. It was sort of like fidelity, given some state rho, you want to find the closest sigma A tensor sigma B, so the closest product state. So I kind of have some results, but I can't prove it. I can show that, I think I can show it numerically works. Yeah,
okay.
But it's, yeah.
Oh, good.
So any other questions?
Yes, anyone else? Okay, I guess I just have sort of like just curiosity. So like in your proof, like it's very nice. Like you sort of have to just fit in the correct A and C.
Yes.
Yeah. But you did say that, of course, actually finding like getting to this point could be. So how long is this like months of work?
It took me 2
weeks?
months. It took me 2 months.
Okay.
No, actually one. That's not true. The first month we found slightly a very complicated proof, which used like I was copying somewhat like taking some ideas from a different paper from operations research. But then I realized, so this is an important thing actually. So I realized that these operations people do this with this kind of tools using statistics and stuff and prove it. But then later on I realized, you don't need all of this. You can just use like some nice properties of fidelity. So that happened a month later.
Okay.
Yeah, so actually I think if we could communicate with like operations research and math folks, they would probably be interested in the fact that this thing that they have been proving using like statistical tools and everything, I think something called statistical distance or whatever, you can actually do it by very basic matrix operations. So that could be interesting, but we'll see.
I mean, of course, like they will use tools that they are familiar with, and I guess like this kind of fidelity things is not really the sort of thing they think about. So
yeah, absolutely, yeah. Yeah, it's funny because it's exactly in the form in which we discuss fidelity, right? Like that's how the expression they were interested in. It's just like average fidelity. So yeah.
Yeah. All right. So yeah, maybe one final chance for questions. Okay. If not, I think like I will stop the recording. But I guess if people still wanted to ask questions, they can stay. But I guess we can end the presentation officially here. Okay. Thank you again
No, of
for the
course. Thank you,
interesting
guys.
talk.
Thank you. It was a pleasure.